Hey, greetings and welcome. This is At One with Zero. Welcome to our neighborhood. In today's episode, what we're going to do is hammer out some equations for drug absorption and elimination. This is assuming that a person ingests a drug every so often at regular intervals, like once a day. Starting out with once a day, but you can always change it to like 3 times a day or whatever. Um, So this first cell here, what this is, temp 1 is going to be um, solving a differential equation. It's desolve is solve a differential equation. Let me make this bigger. Too big. Okay, try that. So temp 1 is this. What I'm trying to say is that C is the concentration. It's a function. C is 0 equals 0. That means the initial amount when time equals 0 is 0, or 0 concentration. And then the derivative of C, the rate of change of C, is 1 over x if t is in this interval. X is the time to peak concentration. And I'm saying that the initial concentration peak is 1, a unitless 1. Over x, so that means in x units of time, the concentration reaches 1 unitless 1, and then if t is less than 0, it's going to be, the derivative is 0, so it's flat, and otherwise if t is greater than x, or equal to x, then the derivative c prime equals k1 times c of x. That means that the rate of change c prime of t is proportional, k1, to the concentration that's there. And that assumes that the kidneys and liver are functioning correctly, so they're not storing all this drug. So let's see how long it takes to solve the differential equation. You'll see this outer bar that's blue here. You'll see it turn yellow when I execute it, and then we'll all see like how long it takes. So the yellow bar here on the side means that it's running. You can also look up here. It says running. So here's what it says. The concentration is e to the k1 times t minus x if t is greater than or equal to the time it takes to get to the peak concentration. And otherwise, the concentration is given by t over x, and that's for otherwise. So that's for t less than x. Okay, x, remember, is the time to peak concentration. So then I want, when time equals the peak plus the half-life is h. When t equals that, I want it to equal exactly 1/2, a unitless 1/2. Let's see how long it takes that. So it says h is greater than, not equal to 0, and k1 equals this. Good, so we got k1 out of that, and when you plug it all in, the exponential e and the logarithm kind of cancel out, and you're left with 2 to this power. Now, what this is showing it here is this horizontal line is just 0.5, unitless 0.5, and it takes 4 hours, let's say, to reach the peak, which is 1.0. The peak defined to be 1.0 after the first dose. That seems to work out pretty good. And now these two curves, the green one and the, like, I don't know, orange or dark mustard colored one, they're nearly indistinguishable. And one of them is assuming that the drug, while it's being absorbed, starts being eliminated, and the other one is a straight ass rise in concentration. And since they are very close, I'm just going to go with the simpler one, which is this. And now I could have gone with this, and that does take into account that when you're absorbing, you're also starting to eliminate, but it doesn't seem to matter much. This is a case where the time to peak is 4 hours, and the half-life is 20 hours. And I'm just going to plot these two. So the blue one is you take the drug at time equals 0. So the horizontal axis is time. This is 24-hour. These are hours, so it's up to 72 hours. And the unitless concentration peak after first dose is 1, a 1.0. And then what I did is I this part, for the mustard one, concentration of T minus 24, that shifts everything forward 24 units. And I'm looking at time going from 0 to 72 hours. Now let's try this. I'm not only going to give the two plots, one the original concentration and then the concentration shifted, and then I'm going to add the two. Okay, and we'll see what happens. So still these colors are not ideal, but it's because the graphs overlap. And the green one here and the mustard one here are exactly what we had before with the blue and the mustard. But now we have green and overlapping the blue, and except for here after 24 hours. And this one that goes up to 1.4 is the sum of the two. Okay, so now we're just gonna keep adding. All right, shifts, and you can see the blue one on the top is climbing. It's the sum of all previous amounts. So here's the major accomplishment, I guess, is that you can look at the sum of all the concentration, T minus 24K. That means there's a new dose every 24 hours. And if I add them all up, I get something pretty interesting or cool. So it's running that right now. I'm asking it to simplify an infinite series. K goes from 0 to infinity. And there we go. Okay, so before you reach peak concentration, this is what you get. And then for T greater than X, you get this thing. Okay. And that's pretty cool. So that's not a like, it's not easy to remember, but it fits like in one page, so it's not too bad. So then I just copied these results and put it here. So I'm just gonna run that, and then what this is showing is that so when time equals 0, time is a horizontal axis. These are hours, so 50 hours, 100 hours, 150 hours. This is a unitless y-axis. 1.0 is the normalized peak concentration of one dose. And then it fades away when you eliminate, and then you take another one in 24 hours, and it bumps up. But it doesn't bump up that high. And then it bumps up, and it seems to stabilize into this pattern, okay? And of where you're eliminated as much as you're going to eliminate, then you take another dose, and you go up again. So then I wanted to look for formulas for what is this peak here, and then what is this trough here. All right, it seems to be around 0.5. for the trough, and for the peak around 1.3. So see what happens. I don't need that, or that, or that, or that, or that. Okay, so for cymbalta, the peak time to peak concentration is 6, and the half-life is 12. These are averages. So I'll run this. That was quick. Okay, so the mustard one is the level of the trough. Let me make this picture easier. Okay, so by the third dose, they're at the peak. So one of these many dose concentration is the wiggling graph of concentration. This I think is the I don't know, I don't remember. The trough, I think. The trough number is that, and then this is the peak number. And then the mean of the two is shown as the red bar. Okay, so that's the average amount of the concentration you have in your body. I just look like I'm doing it all over again. But that's pretty much it. Yeah, I can't find anything else. Alright, cool.